Hello, everyone, and welcome to today's webinar, From Design to Implementation of SARS CoV-2 Diagnostic Testing. I am Michelle Ashton of LabRoots, and I'll be your moderator for today's event. Today's educational web seminar is presented by LabRoots and brought to you by Abbott Scientific Affairs Molecular Diagnostics. To learn more, please visit the Sponsored By tab. Let's get started. Before we begin, I would like to remind everyone that this event is interactive. We encourage you to participate by submitting as many questions as you want at any time you want during the presentation. To do so, simply type them into the Ask a Question box and click Send. Questions will be answered during the presentation and also via email following this event. If you have trouble seeing or hearing the presentation, click on the Support tab found at the top right of the presentation window, or report your problem by clicking on the Ask a Question box located on the far left of your screen. This presentation is educational and thus offers continuing education credits. Please click on the Continuing Education's Credits tab located at the top right of the presentation window and follow the process to obtain your credits. I now present today's speakers. Dr. Gavin Cloherty, Head of Infectious Disease Research at Abbott Diagnostics. Dr. Frederick Nolte, Professor and Vice Chair, Laboratory Medicine and Medical Director of Clinical Laboratories and Molecular Pathology, the Medical University of South Carolina. And Dr. James Kirby, the Associate Professor of Pathology at Harvard Medical School and Director of the Clinical Microbiology Laboratory at Beth Israel Deaconess Medical. For a complete biography on our speakers, please visit the Biography tab at the top of your screen. Our speakers will now begin their presentations.
It's a real pleasure to be here today and to have the opportunity to present, the design and development concepts and implementation of our SARS CoV-2 diagnostic tests, and to share this presentation with Dr. Nolte is also a great pleasure. When I was given this title of a talk, I decided to take the approach in developing the talk of just putting you in the context of what we were thinking as this whole pandemic was unfolding before us, and how we went about approaching the the development of diagnostic tests. So real quick, let me walk through these preliminary slides. So the mandatory disclaimer, I'll leave that up there for a second. And obviously the title of the talk is the Design and Development of SARS CoV-2 Diagnostic Assays. The learning objectives for this talk will be talk a little bit about the SARS CoV-2 disease and the virus, a little bit about the molecular assay design and development, and also the serological. I'm going to focus on the core lab assays, which we were more directly involved in, and not on the rapid diagnostic point of care tests that we're more peripherally involved in the development of those guys. So we're going to review the challenges and again of the nucleic acid test development and serological test development, as well as talk a little bit about the what we're learning about this virus as we go along. So then, to get into the talk in earnest, we'll start off by looking at the SARS-CoV-2 virus and disease associated with it. And if we look at this slide, I think you see it in context. So it's not the first SARS-CoV coronavirus that we've seen. Obviously, we share this space with the normal beta coronaviruses, the 4 strains that cause the common cold. But the first SARS that came around in 2003, I think it killed about 700 or 800 people. I think the numbers vary very slightly. But the mortality was about 9.5%. If we look at MERS, the mortality was significantly higher at 35%. and now we see the SARS CoV-2 mortality is about 7%, and that the exact numbers above that are kind of changed daily. And these numbers were taken from the end of April, so obviously things have changed since then. I think it's interesting that the initial SARS-CoV did burn itself out. MERS still kind of percolates a little bit and pops up every now and again. But this current outbreak of SARS-CoV-2 has really become a pandemic. So the different biology or natural history of these viruses are slightly different, but what is similar or the same is the importance of the diagnostics. So the importance of accurate and timely diagnostics in identifying cases that enable a rapid reaction both clinically and from the public health space is critical. I think on the right-hand side of the slide you see a quote from the EU Commission. So this illustration just shows a normal, kind of immunological response and virological response to an infection with a normal virus, what you would expect. And this, the reason for putting this slide in here is to kind of present you with what we were thinking, but we were very much conscious of the fact that we didn't know this was a new virus and we couldn't make any assumptions. But if we had to make an assumption, here's a starting point. And this led us to focus initially on the most urgent clinical need, which was the identification of people who are actively infected in that acute phase that would need to be done with a molecular test, with a direct marker, so a molecular test for the viral RNA. Later we can, maybe in another talk, we can talk about antigen. But, and then following on that, we knew that the most pressing question would be who's recovered, who might be able to go back, to work, or those kind of key questions that people have. So we focused on the IgG response next, but we also didn't want to mask any information. Again, we didn't want to be like, I use the term arrogant to think that we would know everything about this virus, so we can just lump all of the serology together. So we separated out the IgG and IgM development work streams to make sure that we could have the most granular information about the patient in front of a physician or the population that a public health system was facing. And so that'll bear out, and you'll see a little bit more about that in the slides that follow. So our thinking, I think which is bearing out, was that if you look at this slide here, it shows the different molecular and serological markers and what they might tell somebody. So if you've got a PCR positive on its own, it's most likely the early acute phase where the body has not mounted an immune response, at least enough to be detected. Moving into PCR plus IgM, you're in that kind of middle phase where normally PCR will start to wane a little bit and the IgM will start to come up. So you usually within the first week of symptom onset, first week or two, but your IgG is still negative. You can have that spot where IgM is the only marker that's positive, and this might be in within again the first week or so, and there may be a day difference or two as what we're seeing between IgM and IgG coming up positive, but that might be an important thing to note, because if you didn't do that IgM, both would be negative and you might miss that case. And actually there are cases when all three are positive, because we're finding that IgG is a very sensitive marker that comes up quite early. And then there are other permutations where PCR and IgM can be positive if you're in the late stage of infection, or maybe there's a miss by the IgM assay, or just again you get into the later phases where serology is only positive. In the end, IgG is the most durable marker that would indicate for exposure and a past infection. So this slide here, I pulled this graphic from a very short review paper, Suderman et al. In JAMA. It was online at May 6th, and it's an interesting one. And it's only a short paper, so I'd recommend it. But what it shows is how different this picture, or what's important, I think, is how different this picture is when you compare it to what we expected or could have expected in the previous slide. You'll note that the RNA detectability definitely differs in the course of infection and by the sample type, whether it's nasopharyngeal, nasal, a throat, sputum, or whether it's a stool sample. whether or not you'll be PCR positive depends on that sample type and also when this sample is taken. Also surprising, well, maybe not so surprising because we saw a similar thing with SARS, with the original SARS infection, is that IgG and IgM come up at almost the same time. There may be a day or two difference. We'll talk about that a little later, but IgM does drop off more quickly than the IgG, which remains positive. And an important note is that this virus has only been in the human population for a couple of months, so that's all we can tell is how long these markers last is in that limited time period. Here we look at some of the potential uses for diagnostics where they could fit in. So initially, for diagnosis, the most critical one is the molecular test, the PCR test, which is the gold standard for identifying those patients who are ill and actively viremic. An antigen test may have application there. It would definitely depend on the format and the sensitivity. And then antibody testing can have an application, and we may have a slide on that later, but just in terms of if you're in that spot where the PCR may be waning and the serology may be becoming positive, it may have the ability to pick up some incremental positives there. There's a use for diagnostics in discharge, and this is actively in debate exactly what that should look like. This current European Commission guideline recommends an RNA test, so consecutive negative RNA tests. But you could also complement that with serology. So if you're negative with your RNA, and you have, let's say, an IgG response, that might give you greater confidence, particularly if it's a robust IgG response in releasing somebody. And obviously for serological surveys, for epidemiology, for understanding who has been infected, really the main marker for that would be serology and IgG, particularly because it's the most durable marker. So you can see who has been infected and how that is changing at the population level over time. Moving on to this slide, I think what's important, we showed some slides previously that had the normal virological response, what we're seeing in general with the SARS CoV-2, but this slide really illustrates that it's a personal journey, and it will, from a serological perspective, change person to person. So you see 4 different subjects here. Some of them, the initial 3 are more normal. In subject 1 becomes positive after several days of symptoms. Subject 2 would become positive after almost like 13, 14 days. It takes that person to become positive. Subject 3 was positive right from the initial time point at day 12. But in subject 4, where you've got an immune-compromised patient, it was a transplant patient, they did mount an immune response, but it was later. And I think this is something to keep in mind when you see negative results, let's say 14 days after symptom onset or more. You really have to look at what's going on with that individual. And it's I think a specific test is the silver bullet. You've got to look at the entire, all the information you can and the clinical picture in front of you to make a diagnosis and understand what's going on. On the right-hand panel here was pulled from a paper. I think it was Tan et al. But what they looked at was the different response in patients who were critically ill, and that was defined as being on a respirator or not critically ill. So they would have been not on a respirator, but would vary from ambulatory on up. But what it showed was that the IgG response was significantly stronger in those patients who were critically ill from those who were not. And I think more information will need is coming out on the significance of that kind of robust response versus not. And I think what we may be seeing is 2 different kind of diseases. One is more virologically mediated, and another could be immunologically mediated. So depending on what the immune system is actually doing to the body in a given patient. More on that. Now to talk about the design and development of the different assays that we worked on, and to kind of put you in the mind frame, the space that we were in is what I'll attempt to do here. And this slide just speaks to the different things you've got to do normally when you're developing an assay. And I think many people on the call today will be familiar with that. You know, the bioinformatics, the initial assay design, sample prep, optimization, the kind of evaluation, validation, that the iterative cycles that go on. And just for reference, when we're normally building a test for FDA submission and the normal CE mark, this takes years of iterative process and hard work to get this done. And to put things in context, this slide shows how we accomplished this in weeks. So initially in the ID core, where we sit at Abbott, we were monitoring what was going on in China and looking at how things were developing with great interest and concern. The main thing we needed was a sequence. I think, you know, this was noted previously. You know, that is the starting point for building a molecular test. So I think it was January 20th, if memory serves me, and you'll have to forgive me because, you know, with everything being so condensed, there's a slight fog on the exact dates, but I believe it was January 20th when the sequence became publicly available, and that was the day that we hit go and started designing the primers and probes and getting those ordered for synthesis, and that takes a bit of time. So we had a little lag until we had all of the oligos and in vitro transcripts and everything in place, and that was around February 14th. So that really was when things started in the wet lab development in earnest. And we had a prototype assay available within days, which actually, you know, the point I make on March 5th there was we developed this with a certain enzyme formulation, and then we realized, you know, this would need to be done on scale, and, you know, and it really hit us how much scale that would be needed and how fast this would need to be done. So we reformulated with a different enzyme to accommodate this kind of manufacturing, and I want to tip my hats at this point to the guys in manufacturing who've really, you know, had to step up to meet the demand and do it in really quick time as well. So we did that reformulation and got ready for EUA verification studies by March 14th and then EUA submission. And again, tip my hat to the FDA for making this channel open and for working so quickly to get this done in like a 24-hour period for turnaround and then getting this launched. So this was a whirlwind, as you can imagine. Also, you know, wanted to draw note to the fact that we were developing an assay on really, really limited sequence data. We had, you know, 1, 2, maybe 3 as the days progressed sequences. So we were, I don't want to say flying by the seat of our pants, but because we know what we're doing, but it was definitely a lot of sleepless nights as this was going because things could have gone sideways at any time. We tried our best to mitigate all of this risk by selecting targets. We took a dual target approach, you know, that really is kind of getting to be the gold standard in PCR. We wanted to build in some redundancy in case we saw some mismatches. We targeted nucleocapsid and RDRP because we found that is the most highly conserved stretches is where we found. So in addition to looking at the region like nucleocapsid or RDRP, you can throw those terms out, it's really more important to look at the sequence within those. And as we have the global surveillance program ongoing for, you know, many decades, and this is our stock in trade, we really dug into those sequences to find the ones where we thought would be the best targets, both from conservation now but into the future, as much of a crystal ball as we could try and work to predict. So both of these targets co-amplify in the test. That was the design, and also to include the normal armored pumpkin gene internal controls we have in all our real-time assays into this for additional quality control. So this slide, we look at the target selection that we had versus some of the others that were kind of out around coming out around the same time, and we see that we were in RDRP, so was Charité in Berlin, as was the CDC, and we also had a target in N. But I think more importantly than just saying we were in N and RDRP, it's where we were in these regions is the critical part that needed to prove or pass the test of time. We also looked at E, and we have that as a target region. We can swap in or out if we needed to, but there was no incremental benefit to that. So moving forward, we didn't just rest on those initial couple of sequences. As you can imagine, we were keenly watching how this space was evolving, looking specifically at the target regions where we were. And this slide shows some analysis that was done using GenBank sequences, looking for the primer probe homology, looking at more than 1,300 full-length genomes. And we found that 99.5 had 100% identity. It was 99.5 of the sequences had 100% identity to our primers and probes. There were a few, as you always would expect there will be, that had some mismatches. There was a single mismatch in 6 of the samples to our N target and 1 to RD or P. There was no single sample that had mismatches to both the targets, and none that would have any impact on the assay performance. Again, looking at more sequence, I think this time from the GISAID database, looking at almost 15,000 samples. Again, we found 1.1% contained a single mismatch. This won't impact the test. 0.4 had 2, and 0.007, so 1 out of the almost 15,000 had 4 mismatches, all in one of the gene sequences. And so none of these mismatches or profiles would impact the performance of the test. And that is definitely very reassuring. But now that this virus is with us, it is part of our global surveillance program, so we are actively looking around the world in many different countries and generating sequence and looking at the homology to our primers and probes and the performance of our tests. So this is firmly part of our global surveillance program and our reality moving forward. And looking at some of the performance data broadly that has been done with this test, it's very gratifying to see that the clinical correlation across all sites is greater than 95%. We haven't seen any cross-reactivity, and we've confirmed 100 copies per mil or greater. By that it probably means less. So, it could be 100 copies or less as the limit of detection. So we've seen some, like in the University of Washington, where we've got 93% pickup at 25 copies. So that's very reassuring. I think if we look at the other sites here, we're seeing a limit of detection of 100 copies being reported with almost 100% positive and negative agreement to the CDC assay and the Luminex assay. The CDC, we have 100% positive negative agreement, and then with the Luminex assay, there was one sample where there was not a difference in the negative agreement. So that's extremely reassuring, both for us in our test, but also for the field. If you're using the CDC or one of these other tests, I think it's very valuable information. Again, looking at the platforms, we developed this test for the M2000, which is the old, I wouldn't say old, but the workhorse that's around the world, many thousands of placements. But also this test was ported over onto the Alinity M, which is the, I guess, new state-of-the-art platform, you'd call it, which has significant benefits in terms of throughput, with about 1,000 tests per day. So it's a fantastic piece of equipment. So we ported that test over onto this platform. If you see here the data looking at the positive and negative agreement, you'll see 47 positive samples were also with M2000 were positive with the Alinity, and there were 2 samples that were negative with the M2000 that were positive with the Alinity M. And these samples had a cycle number of about 40, almost 40, pretty much 41. So that's at the very low end of the dynamic range. So we did see a couple of incremental pickups with Alinity. So the positive agreement was 100%, and the negative predictive value was 96.5. So again, quite comfortable with that data. So in closing slide, what's next? I think it's important to know how much virus is present in a person. Is that important? So RNA quantitation could be significant. If RNA is present in the blood, and how much could be an important question to answer if we link that to clinical progress or the clinical picture. From the serology perspective, the key question, does antibody positivity equal immunity? Does how much antibody is present, does that influence immunity or disease progression, clinical outcomes? When vaccines are developed, I think it's important, quantitation could become extremely important if we look at hepatitis and other vaccines where, we need to know if the vaccine has elicited a response that would confer immunity or not. Therapeutic interventions, whether they be monoclonals or other, what impact will that have on the diagnostic tests, and what role will the diagnostic tests play both in the development and the utility of those therapeutic interventions. And then the ongoing epidemiology, whether it be surveys or surveillance, I think is critically important. And on the right hand of this picture, I think it shows, I like it because it illustrates kind of where we're coming from, where we were, where we are, where we're going to, from the reactive clinical management, at the outset of this pandemic, and that's still extremely important as we still have people coming in who are infected today. But expanding out to look at the population level, looking for hotspots, seeing how that's changing, allocation of resources, how will diagnostics and the ability to understand what this virus is doing as the pandemic evolves, and being able to answer these questions and look at things critically, I think will be important moving forward. So with that, I think that's the end of my talk, and I want to thank, again, for the opportunity to talk to you today and present. I'm very happy to have been here, and I hope this was an informative talk for you.
I just want to take a moment to thank Abbott Molecular for asking me to participate in this webinar. My name's Frederick Nolte. I'm at the Medical University of South Carolina. I'm Vice Chair for Pathology and Laboratory Medicine and Medical Director for Clinical Labs. And what I'd like to share with you folks today is our clinical laboratory response to the COVID-19 pandemic. And we'll go through the standard disclaimers. I won't read these, and the audience knows that the support for this program is provided by Abbott. I am presenting at the request of Abbott, and you can see all the disclaimers regarding the use of the tests that I'm going to be talking about from Abbott. What I plan to do in the next 25 minutes or so are review the particular challenges and successes that we have had in responding to the increasing demand for diagnostic testing for SARS-CoV-2. I'm going to spend most of my time talking about nucleic acid amplification tests for detection of viral RNA. I do have one slide at the end that touches on our serological testing for the detection of antibodies. We have a orthogonal algorithm that I think may be of interest to the audience. And I'm spending a lot of time describing our experience with the Abbott M2000 SARS coronavirus 2 EUA assay. And if you'll just permit me a moment to share a personal reflection. This is deja vu all over again for me. This is a publication that we put it together in 2003. But it is in response to the first SARS outbreak. And you all remember that in November of 2002, there was an outbreak of atypical pneumonia with a high fatality rate that emerged in Guangdong province in China. That became known as severe acute respiratory syndrome, and the virus became known as the SARS coronavirus. It quickly spread to 5 continents, and by the time it burnt itself out in 2003, WHO estimated there were 8,400 cases and approximately 812 deaths. So why is this relevant, this publication? Well, at the time, we didn't know what the first SARS outbreak was going to look like. The U.S. was largely spared any big impact with that, but we were in a situation where first time in my professional career, when a new virus emerged, immediately genomic information was available and shared. Molecular amplification assays to detect the virus were there, and we had no idea what the future was going to look like when it came to SARS. So we took it on ourselves to develop and validate 2 laboratory-developed tests. We put them through their paces. We had access to the appropriate reference material, both commercial and from investigators around the world. We were able to contrive samples. We were able to do the clinical validation piece, the analytical validation piece, and we did it very quickly. And I want to just keep this in mind that this is in 2002, it's now 2020, and some of the challenges that we are facing now in response to the second SARS coronavirus problem weren't there in the early 2000s. So keep that in mind. And also, I'm kicking myself a little bit. I had the foresight in 2002 to be prepared before the emergency or before we knew this was going to be a public health threat. I was a little behind the curve for this one, the current one, as were many other laboratories. So what I'm going to do is try to tell a story with the next few slides and take you through the, one lab's experience, the evolution of molecular testing capacities for SARS CoV-2 here at the Medical University of South Carolina. So early in the pandemic, all testing for persons under investigation was conducted at our public health and CDC laboratories. And it was all coordinated through our local epidemiologists that were tasked here from the State Health Lab in Columbia. So as you might imagine, the surge capacity of the public health lab and the CDC for testing was quickly exceeded. Our initial plan here at MUSC was to offer the only EUA available at the time, the CDC test. This is our first issue with supply chain. We purchased the reagents, the required instruments, we got the right reference material to validate, but we couldn't get the needed instrument to perform the test. The ABI 7500 FastDX, we didn't have one available in our laboratory. We placed an order. We learned that the instruments are shipped from China, and so the boat was on the instrument was on the slow boat from China, and took several months. Took 2 months to arrive. We also realized while we were waiting for it, and with the increasing demand, that the CDC assay really wasn't going to provide us with the testing capacity that we needed to support the demand. So our activities really ramped up here around mid-March, the 13th of March. MUSC has tremendous capabilities in the telehealth arena, and we leveraged that capability and expertise to facilitate evaluation and scheduling of local patients and healthcare workers for testing at a remote specimen collection site. We made the decision that we didn't want to bring these patients into the emergency room or the clinic because of the risk of transmission in those environments. So the testing capacity at the time we opened this of the large national referral laboratories was stressed with long turnaround times for results. We had no local testing capacity because we were waiting for the delivery of the ABI instrument from China. So we were forced to use a regional commercial laboratory for testing to support that collection site. But unfortunately, they lacked the experience and capacity to deal with the demand in a timely fashion. So here's where the story gets interesting with respect to Abbott. So shortly after we opened our first remote collection site, I was approached by Abbott Scientific Affairs asking me if I was interested in taking a look at their EUA assay on the M2000. I responded very quickly, and I said yes. There are a number of reasons why it was a great fit for us. We have been an Abbott M2000 user for over a decade. We had 2 instruments in our laboratory. Abbott offered to supply us with a third M2000. The speed by which we got everything done was unprecedented. Basically, in just over a week, we went from having the reagents to having the test validated and bringing it online. So we started collecting specimens from patients in an organized fashion on the 13th of March, and we were live with the Abbott M2000 on the 23rd. This, obviously, we went from 0 to about 1,000 tests per day capacity in a matter of a couple of weeks. We say our turnaround time is in the 24 to 48 hour window, but in reality, the average turnaround time for specimen receipt to result is typically 12 hours for us. Our initial attempts to dilute genomic RNA in universal transport media and viral transport media resulted in poor and inconsistent recovery, which was a bit of a surprise to me, but I guess I shouldn't have been surprised by that. However, the same dilutions of the genomic RNA made in saline showed excellent recovery down to as low as 10 copies per mil in our initial range-finding experiments for the limit of detection. This just shows that the data for that dilution series and the crossing numbers done in the quadruplicate and the mean crossing numbers. So the coefficient of variation of the crossing numbers range from 1.3 to 4.7, depending upon the concentration. So the next step was to look at some of the other commercially the commercially available material that was there for us. We used the exact diagnostics and the SeroCare reference material, both of which have been quantified by digital droplet PCR. This just shows you that they all worked in the M2000 assay. It gives you the expected concentrations and the the crossing numbers for those materials. To confirm Abbott's limit of detection claim of 100 copies per mil, we diluted one of the SeroCare panel members and tested it 20 times at a nominal concentration of 100 copies per mil. All 20 were detected with an average crossing number of 26.7. The clinical verification of the assay started out with the residual clinical specimens that were collected during the early phases of our opening of our remote collection site. So they were collected from March 12th through 17. All of the specimens were sent to a regional commercial reference lab for testing by the CDC EUA assay. We tested the specimens locally with the BioFire respiratory panel as well. We were also able to acquire 10 positive specimens from our local public health laboratory that had been tested by the CDC assay. And then we had finally received our instrument, our FastDX instrument. And since we had all of the reagents on hand, we did a local lab comparison, if you will, of the CDC EUA assay performed at MUSC with the Abbott results. So we did that with 12 positive and 12 negative specimens. So that comprises a clinical verification data set or specimens. So we did 183 residual NP samples. So we've been through these 2 points. The problem is when we looked at our agreement with the regional referral laboratory, it was less than ideal. The positive present agreement was only 75%. There are a small number of positive specimens in this mix. The N1, N2 cycle thresholds in the CDC test were, for the false negatives, are listed here, and they're in the 30s, low 30s to high 30s. I'm not sure what to make of that. The referral laboratory also reported 3 inconclusive specimens that they were unable to reproduce the results. They tested negative by Abbott. So faced with this, we wanted to do a better job of looking at the how well the Abbott assay compared to the CDC EUA assay. So The 12 specimens that we received from our local public health lab, they were randomly selected, and the positive and negative predictive values were 100%. So looking at the second bullet point here are the locally performed tests. The first bullet point is what we got from the public health lab. In both cases, the positive predictive agreement was 100%. So overall, if you put all three data sets together, we found a 91% positive predictive agreement and 100% negative predictive agreement between the results of the CDC and the Abbott test. But we did see the positive predictive agreement was dependent upon where the test was performed. So there is some interlaboratory variation in that in terms of how the results compare to the CDC EUA assay. The clinical verification also included comparison to the respiratory virus panel results from BioFire. There were 168 specimens that were concordant negative for COVID, for SARS coronavirus 2 RNA. We found other respiratory pathogens in 71 of those, or 42%. And I'm not going to read all of the different viruses we recovered, but the important thing is highlighted there. In this data set, there were 18 specimens that were positive for seasonal coronaviruses, which was actually quite interesting because that's more positives than we had for SARS coronavirus 2 in this data set. And from this, it allowed us to pretty robustly say that the Abbott assay was free of cross-reaction with seasonal coronaviruses, as well as the other common respiratory pathogens. So that's basically what we did for the initial analytical and clinical verification of the assay on the M2000. So this is kind of the end of the M2000 story and where we are to date. Not that we're through with the M2000s, but this is where the M2000s have gotten us to date. So since we went live on the 23rd of March, we have performed almost 44,000 tests from individuals throughout South Carolina and identified 2,000 patients. Our current positivity rate, taking all comers, is at 4.36%. You can see in the panel over here the steady growth in positive patients per day. The test positivity, since we're serving this heat map over here, shows the different locations that we are serving and the number of positive patients in those zip codes, if you will. And the darker red indicates the higher percent positive. And that percent positivity rate from the patient populations we serve ranges from a low of 2.85% up to a high of almost 11%. We are the second leading provider of testing behind LabCorp in the state of South Carolina. We're quite proud of that. Finally, yes, light at the end of the tunnel. The Abbott Alinity. We have one of the early instruments. It's been with us for a couple of weeks now. We're finally at a point where we are able to start the validation process. I'm going to share that limited data with you in just a moment. But the reason that we're so excited about it is it's basically the same assay that we've been running for the past 4 months on the M2000. But the design of the instrument and the way, the functionality, and the throughput is phenomenal. So basically, we expect to get as many results out of a single Alinity M instrument as we do out of all three of our M2000s. The analysis time is much shorter. The random access and the stat functionality will help us with those demands for urgent results. There are a lot of other good things about it, but it really is, we're really quite pleased to have it and hope to go live with it this Friday, actually, as soon as we get some of the IT issues squared away. Just again, this data I'm going to share with you is very preliminary. It's the basis of 2 of our verification runs that were done just a couple of days ago. The first was to document the limit of detection, again using the Accuplex verification panel as a source of material. We diluted that down to the following, the nominal concentrations from 25 to 400 copies per mil. You can see at the 100 copy per mil, which is a stated limit of detection, we hit that 95% mark. We feel that we can probably push that down to 50 copies per mil based on this sort of range finding experiment. So we're going to give that a try on a subsequent verification run. And here is the comparison of clinical specimens run on the two instruments. So we have the Abbott M2000 and the Alinity M results. We had 109 frozen NP swabs that were previously tested on the M2000. We retested them on Alinity. We found a positive predictive agreement of 90% and a negative predictive agreement of 98%. We are currently investigating a little deeper those samples that were reported positive on Alinity, on M2000, but negative on the Alinity M. You can see that the crossing numbers there for those specimens were on the high side, but not extremely high, 27.8 to 31.4. And we did have one sample that tested positive on the Alinity M that was negative by Abbott on the M2000 with a very high crossing number of 40.99. So I know that was a lot, but I'm going to leave you with several final thoughts. Clinical laboratory professionals are in the vanguard of the response to the SARS pandemic, providing accurate, high-quality laboratory results to aid in the diagnosis, treatment, and epidemiology. In this role, we have encountered a number of regulatory, reimbursement, supply chain, logistical, and systems problems that we have struggled to overcome in order to fulfill our calling to provide patient care. We are thankful for reliable industry partners in this process, and I can't say enough about Abbott and how they have supported our efforts. Hopefully, our collective experience will be, our experience here at MUSC will be of value to others dealing with similar challenges, and the lessons we learn as a community will make us better able to deal with the next pandemic. Thank you for your attention.
Hi, my name is James Kirby. I'm the Medical Director of Clinical Microbiology at Beth Deaconess Medical Center, and I wanted to share with you some insights from that we've obtained from SARS CoV-2 testing using the Abbott M2000 and Alinity molecular diagnostic platforms. The speaker program is sponsored by Abbott, and the presentation will be consistent with all applicable FDA requirements. So just this slide is a reminder of emergency use authorization and what that means. So I'll start out with our studies with the Abbott M2000 real-time SARS-CoV-2 assay. So that assay is a qualitative emergency use authorization assay that generates either positive or negative results. But sort of under the hood, it also provides results which can be used to understand quantitative performance of the assays, because real-time PCR assays, as you know, are inherently quantitative, and during each amplification cycle, essentially to some approximation, the number of amplicons is doubled, and there's simultaneous amplification and binding of a probe, and that probe fluorescent signal therefore increases geometrically during each amplification cycle. And at some point, the signal from that fluorescence crosses a threshold. And at least in some systems, we call that threshold the cycle threshold. So it's the amplification cycle number at which that threshold for detection is reached. And the Abbott systems use a slightly different thresholding measurement. It's called the fractional cycle number, or just CN, or cycle number for short. But I'll refer to that as a cycle threshold or use those terms interchangeably. The generation of the fractional cycle numbers are actually very interesting, and I'll refer you to the study by Shane and Clemens if you're interested in more details about how that number is determined. But it's a way to sort of avoid some of the artifacts and fluorescent baselining. Okay, but we don't need to know those details, just that we get this very important cycle number information. The M2000 assay and the Alinity assay that I'll tell you about later, they're both dual target assays, so they're detecting two targets within the SARS-CoV-2 virus. And importantly, the assays have a robust limit of detection. And so, as I mentioned, real-time PCR is inherently quantitative. And so, our goal was then to be able to take this cycle threshold values and convert that into a viral load and see what that could tell us about our testing results in our patient population. So we determined that our limit of detection was 100 genome copies per mil across our 4 different Abbott M2000 analyzers. And the CT value was approximately 26. And, as I mentioned, with PCR amplification, if it's 100% efficient, you know that each cycle number, you're going to double the number of amplicons. So you go from 2, 4, 8, 16, 32, 64, etc. So you can approximate the viral load. So we know that, for example, that 100 is our LOD. So you can use this sort of simple formula, 100 times 2 raised to the limit of the CT at the limit of detection minus the CT for any given assay to come up with an approximate viral load. So, and that sort of makes sense because if your CT was 25, that means you're basically resulting one cycle earlier. So you would expect that your viral load would be twice as high as your limit of detection. If you plug that into the formula, you get a viral load of 200. If you're one cycle later than your limit of detection, you plug it into the formula, you get a viral load of 50. Well, of course, nothing in life is that simple because amplification efficiency is less than 100%, and it decreases with cycle number. And you could, these are graphs of 2 positive samples, one with a very low CT and one on the right with a very high CT near the limit of detection. And you can see that there's more sort of, the slope is steeper with a sample with a very high viral load that gets detected earlier. And as you go through additional amplification signals to reach your threshold, the amplification becomes less efficient. By basically looking at a lot of different curves like this, we're able to empirically establish a formula which we think fairly accurately predicts the viral load and from the CT value. And we've sort of published some of this data now in bioRxiv if you're interested in more detail. So I'll just leave it that we think that we have a pretty good approximation of viral load. And so then we looked at our data from March 26th to May 2nd. And, that was sort of our big surge in the state of Massachusetts. So we did 27,000 tests. We had 6,000 positives, 4,700 unique patients. And so we had 2 questions. So for a viral load to mean something, one of the questions was, well, is it repeatable? If you swab someone's nose, and you did it twice in a row, and you got a viral load of 100 one time and 100 million the second, then viral loads would not be clinically useful because they wouldn't necessarily mean anything. And the second question was, can we learn anything from the viral load distribution, and would that help us understand how to use our testing? So in fact, the CT values, and therefore the viral loads, are reproducible between nasopharyngeal swabs collected across short time intervals. So in our very large data set, we had a bunch of patients who had repeat collections either within 6 hours or within 12 hours of each other. We don't know the reasons why. And then we plotted the CT value from the first collection versus the CT value of the second collection. You can see that we have a nice sort of linear relationship throughout the range of CT values that we would obtain. So it looks like those CT values are repeatable in a clinical sense if you sample patients more than once. So they're telling us truly about a status of our patients. Okay, so then we decided to, basically we converted our CT values for patient first positives, and so that's about 4,700 patients, and we basically binned those viral load results and to show the fraction of cases in each 1/2 log 10 bin. And so our viral loads range from very low up to 1 billion copies, genome copies per mil. And one of the fascinating things was that the distribution was fairly even. And so you see basically about the same number, a fraction of cases are distributed throughout the range of detection, except for, a drop-off below 100 copies per mil, which is the limit of detection. So we considered that was reflective of the limit of detection of the assay rather than an actual change in distribution. So why this occurs biologically is not clear, and perhaps is hand-waving, but it may reflect the fact that virus is replicating logarithmically somehow with burst sizes that spread out and infect large numbers of cells sort of consecutively. But in either case, what that sort of allowed us to do was then plot sort of a cumulative distribution. So essentially what we're plotting here is at every point on the x-axis is sort of the fraction of cases that would be caught above a certain viral load. So, for example, approximately 80% of the results that we would expect would be caught with a viral load above 10 to the second genome copies per mil. And so based upon sort of these results, what we did is we sort of extrapolated with a red dotted line to say, if we could detect consistently basically a single virus in a reaction, what would that be? And if we made that extrapolation and considered that ideal detection of 100%, then the Abbott assay would detect about 90% of those patients. So what I think is very important to consider is if you sort of look on the x-axis and then consider the reported LODs of different assays. So for example, the CDC assay has a limit of detection of 1,000 or 3,000, depending upon the format that's used. The GenMark EUA has a limit of detection of 1,000 as reported in the literature. LabCorp about 6,000, and the Sophia antigen test above 1 million if you sort of do convert the units they use based upon their reference material that they use for their calibration into genome copies per mil. So, these, where you place these numbers, there's probably some play, but I think the important point is that as you increase your limit of detection, you significantly affect the fraction of cases that you detect. So, for example, with the Sophia antigen test, you might expect that you would miss more than 50% of the cases that you might detect with the sort of best-in-class PCR methods. One of the things that I should mention, and one of the problems in the field, and again, this is early and we're in a crisis situation, is there's no standard, there's sort of no reference standard. And a lot of these, for benchmarking your assays, so the limit of detection and these reported limit of detections have been determined using different reference materials. So, I would say that, take this graph as an approximation, and there's clearly a case for some universal standard for benchmarking so that we as a clinical community can really understand the differences between these assays. Okay, when all this happened, it was a chance to review sort of the anatomy of the nasal passages. We have nasopharyngeal swabs, which proceed backwards into the, basically all the way back to the nasopharynx in red. We have nasal swabs that sample more interiorly. And importantly, the anterior nasal passages are lined with squamous epithelium. The virus replicates in ciliated respiratory epithelium. So there's some theoretical concern that anterior nasal swabs may not necessarily sample the right place. So we know that nasopharyngeal swabs appear to have the best sensitivity, and they clearly sample respiratory epithelium. However, they're difficult to collect. You need trained collection staff, and they're uncomfortable. We don't have people that want to come back and volunteer for repeat testing unless under duress. Nasal swabs are easy to collect. However, they may not fully sample the respiratory epithelium depending upon their depth, and there's difference in the literature regarding performance of nasal swabs. So we performed a multi-arm clinical trial to compare the performance of nasopharyngeal swabs to nasal swabs in our patient population. And we basically, shown in this graph, are the CT values with the nasal swab and the CT values of the nasopharyngeal swab. And anything that which was negative, we're reporting out as a CT value in this graph of 37. And so you can see that for nasopharyngeal swabs with CT values starting at about 21 and especially going higher, that we're missing a lot of nasal swabs. And if we sort of plot this out, and this is a graph showing concordance using a kappa statistic between nasopharyngeal swabs and nasal swabs. These are done in parallel at the same time in each patient, in that, above 1,000 genome copies per mil, there's very good concordance, but it rapidly drops off below 1,000 copies per mil. So where does that leave us? And what's the use of nasopharyngeal swabs? Well, first, what's the explanation for these observed differences? It's unclear. It may be that if you have a very exuberant infection, it spreads out more in the nasal respiratory epithelium, so it's easier for it to be sampled by nasal swabs, but that's really unknown. One question is, what makes a patient infectious? And I think that's what we're still trying to understand. If you look in tissue culture and just take, for example, the BEI Resources cell culture control material that many of us have been using, the ratio of genome copies to the tissue culture infective dose, or 50% infective dose, is about 10,000 to 1. So you have to have, a lot of genome copies to get a single infected tissue culture cell. And this is similar to what's been observed in patients. So, for example, in the study by Wolfel et al., suggests that the ability to culture any virus from patients appears to occur with viral loads greater than 100,000 during the COVID-19 recovery phase. So what we think is that we should use the most sensitive possible collection technique, nasopharyngeal swabs, in symptomatic patients, in patients who are being admitted to hospitals, and for contact tracing. But the nasal swab, in terms of trade-offs, may be an excellent thing to use in larger screening campaigns of asymptomatic individuals. And locally, we've been having a lot of discussion about, for example, weekly sampling on college campuses and potentially in businesses. And the nasal swab would provide an easy sampling technique that would identify patients who are infectious and could then sort of reflex to further contact tracing with or resampling in let's say, a dorm room that's infected with targeted nasopharyngeal swab testing. In the arms of our study, we compared dry swabs, which were sent to the lab, and anterior nasal swabs and deep nasal swabs, and they appeared to perform equivalently, giving us multiple options. Okay, so I've told you about studies with the M2000 platform shown on the left-hand side of the screen. We were very excited to be one of the first adopters in the United States of the Alinity M platform. So we wanted to get a feeling for how the assay performed against the M2000. So shown here, about 50 positive samples comparing cycle numbers for the M2000 and the Alinity, and they were highly correlated in R-squared of 0.2. We see two samples which had a lower cycle number for the Alinity compared to the sort of falling below that straight line, and perhaps the amplification in those samples were a little less efficient on the M2000. There was a shift in cycle number, so that the cycle number for any given Alinity assay was about 12 CT or CN units higher. That raises no practical differences, and the assays were highly correlated. We also did a limit of detection study, including testing at levels below the claimed limit of detection, and using logistic regression. We estimate the limit of detection is about 45. We didn't do a huge number of replicates, so the black dotted lines to left and right of the red dotted line are the 95% confidence intervals. So a limit of detection was excellent. And just as one final note of the utility of being able to access the cycle number or cycle threshold values, we're able to use those to support a number of different initiatives in our COVID response. And I'm sure that many of you, like us, had issues acquiring certain, basically, supplies needed for sampling patients. So we went into high production to make viral transport media. We made about 3,000 to 4,000 viral transport media tubes a day for quite a long period. And what we would do is we would, for quality control, since we had many batches that we prepared, every time we had a new sort of lot, we would spike a sample of that lot at 2x the limit of detection with the sericare reagent and determine the CT value. And so this is a plot of CT values for different lots over a 30-day period. And so that's a Levy-Jennings plot, and is expected, since we were 2x LOD, for the Abbott M2000 assay, we had a CT mean of 25, and there was pretty tight amplification, showing us that each lot there wasn't some sort of inhibitor that was introduced, and so that we could use those for patient testing. And so that data has been published, and the first reference at the bottom of the figure. And then we also worked with a number of manufacturers to help vet their 3D printed swabs. And one of the questions that we had collectively was whether they were using different types of material to print their swabs. And it was really important to know whether anything would leach into viral transport media and cause PCR inhibition. So we would soak the swabs in viral transport media overnight and then spike the viral transport media at 2x the limit of detection. And again, look at CT values. So we were able to establish whether there were inhibitors that would affect our testing. So that was extremely helpful. So in conclusion, viral load matters, and especially the limit of detection of your assays. You really need to know what they are, and that will impact the percentage of patients that you will detect. I think there's a good case for a universal standard that will allow us to understand how different assays compare. It's hard for one site to bring in all the assays and compare them with the same material. So a reference standard would be really helpful. There's, I think, clearly roles for both nasal and nasopharyngeal swabs depending upon the sensitivity needed. And I think nasal swabs will, find their use in supporting screening of asymptomatic patients. The Abbott assays had robust reproducibility, which supported quality control and quality assurance initiatives in our response. And the sample to answer Alinity M platform shows a low limit of detection and a high degree of agreement with M2000. And we can already see that sort of sample to answer and rapid turnaround time has been very helpful in our helping our hospital system. I'd like to acknowledge a lot of people. Annie Cheng, our molecular supervisor, Tammy Galloway, our molecular laboratory manager. We have an amazing group of clinical laboratory scientists and a lot of volunteers from our research division and elsewhere that have been keeping our clinical lab and pre-analytics and post-analytics going. So I can't thank them enough. Rami Arnaud and the CLS6 COVID research team that have helped with a lot of the studies that I told you about, Stefan Riedel, Associate Micro Director, Ryan Pena, the molecular CLIA holder and HLA Director, and our hospital system, our pathology administration, and Abbott Molecular. And with that, I will close, and I'm happy to answer any questions. Thank you so much.
Thank you all for your informative presentations. We would also like to thank LabRoots and our sponsor, Abbott Scientific Affairs Molecular Diagnostics, for underwriting today's educational webcast. Before we go, I'd like to thank the audience for joining us today and for their interesting questions. Questions we did not have time for today and those submitted during the on-demand period will be addressed by our speakers via the contact information you provided at the time of registration. LabRoots will alert you via email when this webinar is available for replay. We encourage you to share that email with your colleagues who may have missed today's live event. Until next time, goodbye.